Hi everybody, welcome to the Points of Topology NPTEL course. It's a live session for 4. My name is Shavik and I work in counseling mathematics. So there's a wants to join, Mr. Mustaq. So Mustaq, can you please confirm whether I'm audible and is the screen visible to you?
Yes, it is audible and visible too.
Okay, thank you, Mr. Confirmation. Do you have any doubt or any questions from previous sessions or any question for assignment?
No.
Okay, thank you for confirmation, Mustaq. One more thing is that right now I'm putting one link in the Google chat. Uh, Please make sure to submit the Google form because it will be used for attendance purpose. Okay, so please submit the Google form by submitting attendance.
Okay.
Okay, since you don't have any question or doubt, so let me start with from the previous session where you have stopped. Okay, in between, if you have any doubt or question, please unmute yourself and ask. Okay. Okay, so let me start writing. So let's solve the following question. So let's solve the following question. So question reads as follows. One minute. The question reads as follows. Let Y be an ordered set with ordered topology. And suppose it to function f and g from x to y be continuous. So in that case, show that the collection of all those points x such that f of x less than equal to g of x is closed in x. So see, the intuition for this type of solving for this type of problem is as follows. See, in real RC, suppose we have to function f and g from x to some suppose r to the power n to r. In that case, this set will be what? This set will be nothing but um, f minus g whole inverse minus infinity comma close. Now point is that this is an closed set. So in that case, in those situation we can say, but here we don't have real and we have some arbitrary topological space. In that situation, we need to prove all those x as the fx less than equal to gx is closed. Okay, that's what we need to prove. So think about it, take your time and let me know. You need to use the fact that there is some ordering. Of course, you cannot do multiplication subtraction because it is prohibited doing here. I mean, in topology, you cannot simply multiply things, right? So, okay. So think about, take your time and let me know. Sorry. So the hint is that the corresponding hint is try to use the fact that in order topology minus infinity comma x is also closed. So try to use this fact. Okay, yeah, so it's a tricky problem. It's correct, it's a tricky problem. Without the trick it is very difficult to solve this problem in two. Yeah, that's stupid, let's be honest. Okay, so try it. So Mustak, do you have an idea how to solve this kind of problem? Okay, so so it seems to be complicated for you. So let me write a solution. See, so in topology we know that f is closed if and only if its complement is open. Okay, so what we can try to show is that all those x are the fx greater than gx. Consider if you're able to show if it is open, then its complement closed. So what are we doing? We are choosing x naught belongs to x, a point in here. So that implies what? That implies f of x naught greater than g of x naught. Okay. Now we have given the fact that fx greater than gx. So how we can write this particular thing? So we can write it as follows. This particular set can be written as f inverse of g of x naught comma infinity intersection g inverse of minus infinity comma f of x naught. So it's a intersection of open sets in both direction. So that's why they are inverse open. That's why as a whole this union, this intersection is open. So that tells that their complement, that is uh, so their complement, that is this one, is closed in X. So that is the argument. So this theorem tells what? If Y is an ordered set with ordered topology, sorry, then if you have a map from X to Y continuous, then all those X as an fx less than equal to gx is closed. So that is the argument. So in reanalysis, this argument can be achieved by considering f minus g. But in topology, there is no option. But here, order topology plays an important role. Is that open intervals are open. So that's what the advantage of using order topology is. Okay. So that's what the argument is. Is it clear? Okay. So the other student joined. So okay. So those who have joined late. So today we have discussed the following problem. 1 minute. The problem reads as follows. Suppose Y is an ordered set with ordered topology, and if G is a map from X to Y continuous. We need to show all those X such that fx less than equal to Gx. So the solution is very simple. You need to consider its complement, and you need to prove that its complement is open. Okay. So for that, what we have done, basically, finally, what we will get is that if you, yeah, that its complement, if we take a point x naught from its complement, then this particular set can be radiated as follows, and each of this portion is open, so their intersection is open. So that's what the argument follows. Is that clear?
Yes.
Okay. Okay. So since now more students have joined, so okay, so do you have any question from previous session or previous class? Good. Since there's no question. Okay, in case if you have any question in between, please unmute yourself and let me know. Okay. So next question, let me find the next question. Okay. So next question is as follows. Let A subset of X and let F is a map from A to Y. be continuous. Let y Hausdorff show that if f may be extended to a continuous function g a closure to y, then g is uniquely determined by f. Okay, so what does this statement tell actually? So this statement tells that suppose a function f from a to y, okay, and suppose the function f can be extended to a closure. Now the point is that if y is Hausdorff and if the function f can be extended to a closure, then Hausdorffness will automatically imply the extension will be unique. That means if we consider any two extension of f to a closure, then those two extensions will be unique. So that is the beauty of this problem. Okay, is the question clear what we need to prove? Is the question clear what we need to prove? Please don't hesitate to ask question. Okay, so if the question
Means
is yes, tell me.
like it's saying that f may be extended to a continuous function, but
Ha,
f is
yes, if f may be extended.
f is continu.
Correct. F is continuous. Yes. In topology, all maps, everything is continuous. So here it is explicitly mentioned continuous, and extension also is continuous.
Okay,
Yeah. So the okay. So now we need to show that if there are two extension of f to a closure, then those are equal. So that's what the target is. So okay. So first you try it by yourself. Okay, so do you have any idea, anybody, how to proceed or how to show that any two extensions are equal? Any idea? Okay, so the problem is actually a bit tricky. I mean, the solution is a bit tricky. So let me write it down. Okay. So let G1, G2 be two extension of F. That is G1, G2 are two maps from A closure to Y, both continuous, sorry, both continuous maps, and G1 restricted to A is equal to G2 restricted to A is equal to little f. Okay, that's what the extension means. Okay, and we need to show, our target is to show G1 is equal to G2. Note that the domain of G1, G2 is A closure. Okay, so the trick is as follows. We are defining a new map little h from A to Y cross Y. A going to G1A, G2A. Okay, and we are defining delta of Y to be the points Y comma Y. Now Y is given to be Hausdorff by the statement. So this implies what? So previous we have seen that this, so this is closed, so this boundary will be this diagonal will be closed. Why? Since Y Hausdorff. It is a fact we have seen in the previous class. If Y is a Hausdorff, if an always diagonal is closed. Okay, sorry, A is the map from defined from A closure. Okay. Now the point is that since G1 restricted to A is equal to G2 restricted to A, that means what? That means h of this function h of A, this lies within delta of Y, correct? Because h of A contains G1 and G2 both are equal. Now if you take closure, that means we will get what? H of A closure subset of delta Y closure, and we have seen the delta Y is closed, so delta Y closure delta of A, and also H is continuous, so H of A closure subset of this is because H is continuous. So that means what we get that H of A closure subset of delta of Y. This means what? This means G1 of A to G2 of A. So that is the argument here. Okay, is that clear? Is the argument clear? Please let me know.
Can you scroll above
Yes,
a
yes.
bit?
Is that fine? Is the argument clear? Please let me know. I mean, the argument uses lots of things. First of all, the technical thing which you're using is that if a space is Hausdorff, then its diagonal delta phi is closed. That is the one technical thing we're using. Another fact we're using that is being H continuous, so that tells that H of a closure subset of H of a hollow closure. What is that? 1 minute. It got reload. Let's hold down. Sorry.
We are assuming that H is continuous.
No, 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 no. H is not. I mean, H is continuous, but that no need assumption, because this little g1 and little g2, these two things are continuous. That tells that H is continuous. Yesterday, last session we have done a theorem. Now, suppose f is a function from x to y cross z, and if the component function is continuous, then we can
Yeah.
immediately tell. Yeah, so that's why little h is continuous here. Understand?
Yes.
Okay.
Okay, and delta by bar is delta y.
Mm, delta 1 minute. Delta y. What is delta y? Delta being closed because y is Hausdorff.
Okay, so what you were writing here, G1A is equal to.
Okay, sorry for the bad handwriting. So here I am writing, g1 of little a is equal to g2 of little a, and this is coming from this line h of delta closure a, so h of a closed subset delta y, that implies g1 of a is equal to g2 of a.
Okay,
Understand? Is the argument clear? Is the argument clear? Please let me know. Or if you have any doubt, please tell me. Okay, one more thing is that in the Google chat I have shared one Google form. Please do submit the Google form by putting your attendance here, because that Google form will be counted for your attendance in the final mark sheet. Okay, so regarding this particular question, is the argument clear to everybody? Yes or no? Okay, so assuming the fact that this argument is clear to everybody, now let me go to the next question.
sorry,
Yeah, yeah,
means
yeah, yeah, tell me.
maybe I'm forgetting that
Yes,
if
yes, tell me.
like this bar means like it's closed, right?
Bar means it's closure, not
Uh, uh, uh,
closure,
yeah.
correct.
So since H is continuous, then
Hmm.
H of H of closure of A is in closure of
It's
A.
yes, it's a general fact. So 1 minute. So it's a general fact. Suppose f is a function from x to y and a is a sub of x, then f continuous map implies f of a closure subset of f of a whole closure. That is one implication of continuity.
Yeah. Okay. Okay. Sorry.
Okay, so you please go through the argument, and if you get a doubt, please let me know. I'm waiting for you for complete understanding of the argument, and other learners, if you also have doubt in this argument, please tell me. Is the argument clear to you?
Yes, yes.
Okay. Okay. So now let's start the next question. The next question reads as follows. So if be a map from X to A and G is a map from Y to B and both are continuous maps. To show, we need to show that F cross G, the new map from what to where, from X cross Y to A cross B is, is also continuous. So that's what you need to prove. Okay. So that means what you need to show? You need to show that inverse image. If you take open set in A cross B and inverse, you need to show that inverse image is open. Okay. Now the point is that A cross B the product topology. So you, instead of considering general open set, you will consider its basis elements, which are nothing but of the form U cross V, and you could make, you then consider the inverse image of the U cross V under this map F cross G. Okay. So now please try to figure this out, how you can show that if you take any base element U cross V, then U cross V in the codomain side, then how that inverse image will be open X cross Y. So please try to do it. I mean, you need to show that what inverse image of U cross V is open in X cross Y. That's what you need to show. Take your time. Let me know. Any idea how to approach this problem? I mean, just you need to observe that how the F cross G, its inverse image of U cross V will be. That's what the only thing you need to do. Anybody please unmute yourself and tell me. So it shouldn't be very difficult to solve. Don't hesitate to tell. So you can unmute yourself and tell me. No problem. Anybody please? Okay.
We
Yes, tell me.
have to say that,
Yes. Yes, tell me.
let's suppose we have a basis
Yes.
b1 cross b2, and you b1 cross b2 is a basis. Let's suppose b1 is a basis uh of x, and b2 is a basis of y.
Okay.
There,
Then
and 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 then u is an element of b1 and v is an element of b2.
U is the element of. No, no. I mean, so see. I mean, we are choosing U cross V as a basis element from A cross V, right? And you considered B1 is a basis of X and B2 is a base of Y, right? Correct?
No, basis of a, sorry. uh
Okay, yes, base of A and base of B. Okay,
yeah, and so, like, then u cross v is a basis of a cross,
correct.
and we know that,
Hmm.
and we have to show that u cross v is like inverse image of u cross v is open in x cross y. Then we
That's why we
then
need to show that U cross B inverse image open in X cross Y. Correct.
and
Yes, tell me. So the question is, what will be F cross G inverse image of U cross V, right?
yes.
So what it will be? So that will be what? That will be F inverse of U cross G inverse of V, isn't it? I mean, so this is clear, am I right? So if it is not clear, please tell me whether it is clear or not.
Can you give some intuition?
Huh, yes. For example, 1 minute. Okay, so first tell me F cross G is a map from what to what? X cross Y to A cross B, right? And how this map looks like X comma Y going to Fx comma Gy, correct? Right? So this is the map F
Yes.
cross G. Now U cross V, its inverse, it contains what kind of point? It contains all those points x of y such that f of xy belongs to U cross V. This is by definition, right? Sorry,
Yes.
F cross G. and this is nothing but x cross y such that fx comma gy belongs to u cross v. This is correct, right? So we can write this like x comma y such that fx belongs to u, gy belongs to v, and this is nothing but what? All those x comma y such that x belongs to f inverse u, y belongs to g inverse v, and this is nothing but what? F inverse u cross g inverse v. Is that clear? I mean, it's a
Yeah,
set theory argument. I mean, there is nothing to there is not. I mean, there is nothing to intuition to be given. I mean, it follows directly from definition, right?
yeah, okay.
Yeah. Is the argument clear?
Yes.
Okay. So now, since it's clear, and
Yeah, okay, okay. So uh, now since we know that f and g is a continuous function, and f inverse u will be in x
hmm,
is an open set in x, and f g inverse b is an open set in y.
correct,
So therefore f cross g inverse of u cross v will be open set in
correct,
x cross y.
right, correct. Okay. So there is one very tricky problem, mm, which is a use of pasting lemma. So let me recall the pasting lemma, what it was telling. Let me open the previous PDF. So in last class, do you have gone through pasting lemma? Yes, I found it.
I mean gluing lemma you're saying.
Correct, gluing lemma.
Yeah, we gone through last time.
Yes. So the statement goes as follows. So these are, so if x is nothing but a union b and a b are both closed, and f is a map from a to y and g is a from b to y, and if on the intersection of a intersection b f and g both agrees, then the new function h defined by fx when x belongs to a and gx when x belongs to b, this will be a continuous function. So that's what the statement Gaulian lemma is. One important thing we note is that a and b both are closed subset of capital X here. Okay, so that's what the one extra condition we need to. So we need to make sure. Okay, so that's the statement. So there is a one exercise using that statement. Let me.
Yeah, just one.
Sorry. One minute. Let me open it again. Okay. Yeah.
Yeah, can you repeat what gluing lemma say if when A and B are closed in X and
Sorry, can you please repeat the argument?
it, what was the conclusion of the gluing lemma that if
The
A and
conclusion
B
of
are
the gluing lemma is that under this given condition, if F and G agrees on the A intersection B, in that case, the map we are getting H from X to Y, which is F on A and G on capital B, the map H will be continuous. So that is the conclusion of the gluing lemma.
yeah means I want to ask like on what type of problem this gluing
Okay.
lemma is
Okay, so
important.
yes, yes. So there is a one exercise. Let me write it down. So can I change this?
Yeah, yeah.
Okay. So let me write it down. So today we have done an exercise at first, which let me repeat it. That particular exercise tells that if F and G are to map from X to Y, and 1 minute. If F is a map, F G is a map from X to Y with capital Y, uh, there is order topology. Okay. In that case, we have seen that the set X such that Fx less than equal to Gx, this will be closed set. Okay, we have seen this. Okay, now the we have done this exercise previously. Today the first exercise was that, and of course here F and G are continuous map. Now an interesting exercise using this gluing lemma is the following. So suppose H is a map from X to Y, okay, such that H of X equal to minimum of Fx comma Gx. Show that H is continuous. Also given that F G X to Y both continuous. So the exercise is telling us follows. Suppose F and Y are two maps from X to Y, and of course Y has ordered topology. Y has ordered topology. Now we are defining H, which is the minimum of Fx comma Gx. We need to show that H is continuous. Okay. So forget about topology for a second. So we know in case of real line, we know that the minimum of two numbers of A comma B. This is what? This is modulo A plus B by 2 minus modulo A minus B by 2. That's the formula of minimum, right? If I can recall correctly, either mod A minus B or mod A minus A, whatever it is. The point is that this was some kind of formula. I hope, I believe you all have seen this formula. Am I right?
Yeah,
Yeah. Now the point is that Now the point is that in case of real line, I mean in case if our y is equal to r, then we can directly use this formula. But in topology we cannot do addition subtraction, right? But still the same results holds, that minimum of two function is also continuous. We have seen this thing in real analysis also. So but here in topology you need to use gluing lemma, otherwise it is possible, and for that you need to use this previous exercise. You need to use it trickily. There is a closed, you need to construct two closed sets such that the union is x, then you need to use the gluing lemma. Okay, so think about it, take your time. How to construct capital A and capital V so that you can apply the gluing lemma. I don't understand what I'm trying to say.
Yeah, means like we have to construct a capital A and capital E which is closed in X such that we can construct some edge.
Correct, only correct. So and for capital and capital B you need to use this sets x as the fx is equal to gx. That's so this kind of thing you need to use. So think about it, take your time. This shouldn't be difficult.
We have to take inverse image.
I mean, think about just think and consider what how the f and g inverse means what
Set under F.
under f. Okay, then what that will give? That will give nothing. Am I right?
Yeah, okay.
Yeah. I mean, you need to think. Just think about how a and b you can write. I mean, in which situation h equal to f, and in which situation h equal to g, and if h equal to f, then under I mean in which subset of capital X h equal to f, and in which subset of capital X h equal to little g. So think about it, then only you will understand how to apply gluing lemma. Okay, take your time, think about it. I shall be back within few minutes. Okay, so are you able to figure out what our A and B will be?
Like we can, I don't know, means, but what I think that we can consider a number fx minus gx,
Okay.
and consider a, like we can consider a set. For example, if f is a function from x to y,
Hmm.
we can consider a set of all x, so that fx is less than gx.
Okay, so idea is correct, but precisely it is as follows. I mean, yeah, one. Okay, so so we let's write s equal to s1 equal to all those x as that fx less than equal to gx. Okay, and s2 equal to all those x as that gx less than equal to fx. Okay, now already we
Yes,
have seen that these are closed sets.
yes, yes, yes.
Correct.
Yeah.
So so now so clearly hx equal to fx when x belongs to s1 and hx equal to gx when x belongs to s2, and as well as s1 intersection s2 if a point lies between intersection. That means what? Fx equal to gx, so that is the function f and g agrees on the intersection. So blind by gluing lemma, what we can say? We can say that h is continuous. Is the argument clear?
Yes. Yes.
I mean, so if you are in doubt, please tell me, because this construction of s1 s2 is that's the only trick only you need to use for this problem. Correct. Okay, so is the argument clear to everybody? Okay, so I hope it is clear. So let's start a new chapter called connectedness. So all so till now we are in continuity, and I hope that we have done sufficient amount of problems. So now let's go to connectedness. Okay. So first, anybody? So can you please raise your hands who have done the connectedness in metric space or in real analysis? So is there
In
anybody?
I
Yes, tell me.
I did connectedness, but just from physics perspective. Like I didn't take
Okay, so can you please explain a bit?
like just connectedness for
Continue.
Means just there's something like like there are three types of connectedness. Uh, Either it is connected, simply connected, or arc-wise connected.
Okay.
And so I just go through the knife some examples like which I was telling last discussion.
Right. Correct. Okay. So basically, so you might understood the fact that connectedness, as per the name suggests, deals with whether a space is disconnected or not. I mean, whether a space can be broken into pieces or not. So that's what it's all about. And and whatever you said is correct. That in connectedness there are three things. One is simply connected, path connected, that is arcwise connected, otherwise, and usual connectedness. Okay. So have you? So can you tell me the definition of connectedness? I mean, if you can recall at least.
I can just say intuitive definition, means just from physics perspective that
Physics.
like consider a topological space X and 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 if like and if we can sort of like and if we can separate the two, let's suppose x1 is a subset of x and x2 is a subset of x, and if you can separate like x1 intersection x2 is phi, then it is disconnected, otherwise it is connected.
Correct. That's the definition.
So may I?
Yes. Tell me.
A set is said to be connected if it is the union of two disjoint open sets.
Okay. Two disjoint open sets. Correct. Correct only. Correct only. And this is one definition, and there is another equivalent definition. Can you please tell? Can you please recall? So Archa, so the definition which you have told that it is connected if it can be written or cannot be written as disjoint union. What you have said, I can't remember right now. Okay, so uh,
Can't be written
correct,
as.
correct, correct. Okay, okay, correct only. So there are two definition of connectedness. That is, suppose X be a space, then X is said to be connected if X cannot be written as disjoint union of two open sets. That is, if we can write X equal to A union B, where A and B are disjoint and both open, then that will implies that uh, uh, A empty, B equal to X, or B empty, A equal to X. Okay. So that's the first definition. So a space cannot be written as disjoint union of open sets. That means if X is nothing but A union B, where A and B are disjoint and open, then one is empty, another is whole of X, and vice versa. So that's what the connectedness means. Okay, this is one definition. And second definition is that, not the definition, it's the equivalent statement. X connected if and only sets which are both open and closed are only empty set and the full space. So the second definition tells that space connected if the only set which are both open and closed, either the full space or the empty set. So that's the definition of connectedness. Okay. So firstly, before going further, so can anybody please try to show how this second definition is equivalent? That means what? That means you need to prove the second statement from the first statement and vice versa. So try to show that one implies two.
As a set can be both open and closed if it is either an empty set or the set itself. So, by the definition of connectedness, I can easily tell that if it is connected, then I can show it will be an empty set or it is the set itself. So, it is obviously open and closed. In the same way, I'll be proving converse part.
Correct only, correct only. Correct, right. Okay, so that's the definition of connectedness. So there is okay, so that is one thing. And so there is a definition called separation. Okay, so the definition shall look like abstract, but let's let's go forward. So soon we will see some examples. Okay, so the next definition called separation. As per the name suggests, it tells you how to separate 2 points. Okay, sorry, it tells you that under certain condition a space can be broken into pieces, so that can be, so that's called separation. So the definition goes as follows: let, what is this, let X be a space and A be subset of X, then the pair separation, it's a pair, the pair AB is called a separation if X equal to A union B, A, B and this joint, and A, B are both open. Then we will say that the pair AB is a separation of X. So that is the full statement. That is, suppose we have two subsets A and B which are both open. Then the pair is called a separation if X can be written as A union B and the intersection is empty. Okay, so
Like separation means like, do we define some measure on separation, like how much separated or something like that? Or
no, in topology there is no concept like how much separated. The only thing is that they are separated, means their intersection is empty and the union is the full space. And how much separated we can measure only if it's a metric space, because in metric space there is a concept or there is a notion of distance, right? But in topology alone there is no notion of distance. So in topology there is no concept of how much separated. Understand?
Yes.
I think separation is opposite of connectedness.
Yeah, correct. So yeah, so you're correct. So if a space is connected if and only if it admits no separation. Correct only. Okay. So that's the definition of separation. So for example, consider the space R2. Okay. Okay. First of all, R2 is connected. I hope that much you know. I mean, at least intuitively you understand the R2 is connected. You simply, this is not a disjoint piece. But for example, if you consider the parabola, sorry, hyperbola, then this hyperbola is what the equation x square minus y square equal 1. So this hyperbola is disconnected because there are two disjoint pieces. Okay. So that's the intuition. And one more thing I must say is that the definition of separation, the definition of connectedness, these are abstract definition. Okay. In reality, while solving problems, these definitions are quite complicated to use. Okay. So that's why there are some certain sophisticated theorems which we will see today or hopefully next session, possibly today also. There are some sophisticated theorems which will help us to detect some space is connected or not. At least some is connected or not, that we can do using some theorems. Okay. But if you think that this definition you have to use always, so that will be very difficult because these definitions are quite abstract in nature. The point is that you simply can't prove that you cannot write a space as a union B where A and B satisfies those conditions. Okay. So that's why in connectedness chapter there are few more definitions actually to understand whether a space is connected or not. Okay. So the first theorem is as follows.
Separation of
Yes.
X defines that, like like pair A B spans the full set X, right? Means
So separation means just a disjoint piece.
now if
Yes.
hyperbola has, we can think of two solutions when x minus y is 1 and x plus y
Correct,
is,
correct, correct. Two piece, it has two piece, right? So that's
yeah,
fine.
but these two piece span the full R2.
No, no, not R2. It two piece span only full hyperbola only.
But you said that this hyperbola is separation of R2.
No, no, hyperbola is not the separation of R2. Hyperbola, 1 minute. So this is the hyperbola, correct? So these two arcs, arc 1 and arc 2, this arc 1 comma arc 2, this pair, it's a separation,
Of hyper.
correct, of
Oh, I
hyperbola
see.
only.
I see. Not R2. Okay, okay,
Correct.
okay.
And R2 is connected, right? Of course, at least intuitively R2 is connected, right?
Yes. Yes.
So connected means it admits no separation by definition, right?
Okay, okay.
Yeah. Is it clear?
Yes.
Okay. Okay. So there are few definitions, sorry, few theorems on the way. So first theorem is that if y is the subspace of x, sorry, one. So first theorem tells that if C comma D is a separation of x and if y subset of x is connected that would imply y either entirely lies in C or y entirely lies in D. So what does this statement is telling? Suppose a space we have X, okay, and suppose it has some separation C and D, and if Y is a subspace of X which is connected subspace, then that Y shall lie fully inside C or fully inside D. It cannot lie here. So such a thing is not admittable. So that's the statement of the lemma is telling. So intuitively it is clear because Y is connected. If it lie within the separation, I mean if it has portions within C and D both, then it will not be connected, right? Correct?
Yes, sir.
Yeah. So can you please try to prove this? I mean, so what you need to assume that Y has pieces in C and Y has pieces in D, and then from you need to show that Y is disconnected. Okay. So can you please try to prove it? So please try to do it. I shall be back within a few minutes. Okay. So are you able to um, solve this? That is how to show that um, this will be this will lie in both of those directions. Any, any idea or any guess?
Can I try, sir?
Yes, sure, sure.
As C comma D is a separation of X, I can write X as a union of C and D.
Correct.
So here Y is a subset of X and Y is connected,
Mm-hmm.
and so Y is also the subset of C union D.
Correct.
But by the definition of separation, C intersection X can be written as C union D, and C intersection D is equal to empty.
C intersection D is equal to empty. Correct only.
So Y is a subset of C union D. So Y can be the subset of C, or Y can be a subset of D.
Correct. Correct.
So finally, I proved this. Am I
Correct.
right, sir?
Right. Correct. 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 So okay. So what she has explained is as follows. So it's by the method of contradiction. So let's assume that um, let's assume what? Let's assume that one. What? So let's assume that Y has few parts in C as well as Y has few parts in D, so non-empty. Now Y can be written as Y intersection C union Y intersection D. Okay, and of course CD disjoint, that implies Y intersection C and Y intersection D are disjoint. Okay, and so clearly this Y intersection Y intersection C, this forms a separation of Y. Correct. That implies what? That implies uh, y is disconnected. So that is the argument. Is it clear to everybody?
Yes, yes.
Okay. So now, okay. So there's a first theorem. The next
But
theorem, yes, tell me.
in the question, I didn't understand the notation that you write. Like if you go above,
Which notation?
what the C slash, its
No,
equivalence
no,
class.
it is, sorry. Y intersection C is not a null, not empty set, and Y intersection D also non-empty set.
No, above here.
Oh, okay. So you know it is not not equivalent. It is or only either Y subset of C or Y subset of D. It cannot write both.
Okay, oh, oh,
Yeah, understood.
yes.
Okay. Now the next question, next theorem is that X is connected. Okay, one, not this. So next theorem is that f is a map from X to Y, continuous, X connected. That implies f of X connected. There is continuous image of connected set is connected. Okay, so that's what the theorem is telling. So how we can prove it? So you, I mean, so the same thing you have proved in real analysis, I hope. So here you need to show that fx cannot admit a disconnection, sorry, separation. So what you need to assume that f admits a separation, and from there you need to find two disjoint open sets for x and y, correct? So think about and figure this how to solve, how to show. That is, first you need to assume that fx disconnected, and from that you need to show that x is disconnected. So that's the contradictory way you need to do it. So take your time, let me know. It is not difficult.
So are we going to prove this by contrapostal method?
Correct only, correct only. So first you assume that if x is disconnected, from that only you show that x is disconnected. That is the way. Please try by yourself first.
So, the controversy of the given statement is if f of x is disconnected, then x is also disconnected. I have to prove x is disconnected.
Correct, correct.
Can you please wait for 1 minute?
Sure.
Means, for example, consider we have a pair UV, so that UV is a separation of X, and
Correct.
then
Not extra. We need to show what? We need to show first, we need to contrapositive step we need to show. That we need to assume that f x is disconnected. From there, we need to show that x is disconnected.
okay, so let's consider U and V is in Y,
Okay. Not y.
and
We need to show that u and v, it's a separation of fx.
yeah, U and V is a separation of X. Then we have a F inverse U in U union V.
Inverse of.
F inverse of, sorry, okay, sorry.
Take your time, no problem. We can have a 10-minute extra, I hope, because today is Sunday. So take your time, no problem.
As uv is a separation of f of x, I can write f of x as the union of u and v, and the intersection between u and v will not be empty set.
Correct.
So there is some element in their intersection.
Correct.
So I'll be choosing that element as some x.
Correct.
So x belongs to u as well as x belongs to v.
Correct.
As u and v are subsets of x, so u is also a subset of x and v is also a subset of x.
Correct.
And I can tell that uh, x is disconnected. I think I'm.
So what are the separations of x?
What are the separations of x?
Suppose we are saying now that u comma v is the separation of fx. So what are the separation? What is the separation for x?
U and v.
No, no, u and v are separation of fx. This u and v lies within fx. We need to go to x only, right?
F inverse of u and F
Yes,
inverse of v.
correct only. And these are open as well because if continuous, and of course f inverse of u intersection of f inverse of v, that is not correct only. Is the argument clear for others?
Why it is not null set?
That is because u and v both lies inside f of x, correct? Image of f of x, nothing but what? Image of f. So every point of image of f has a pre-image, correct?
Yeah.
So that's why these are not null set.
Means if u and v is a separation of x, then u intersection v is phi is null, right?
U intersection v separate. Yes, correct.
What you wrote here?
No, 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 separation. No, separation means their intersection is. No. One, uh, sorry. Correct one. Sorry, correct one. The intersection is empty.
Yeah.
Correct. Sorry. Thank you.
Yeah. Yeah.
Okay. Yeah. Okay. Fine. So now is it clear? Is it fine?
Yes. Yes.
So now the next. So this particular theorem tells that if we have continuous map and if the domain is connected, then codomain is connected. So that's what the gist of this theorem. Okay. Now then the next theorem tells that these are all if and only if statements. Space X is connected if and only if any continuous map F from X to plus
Sir,
1.
is there any attendance for today's class?
Yes. So in the Google chat, I have shared one Google form. Again, I'm resharing. So please submit that. Others, please also submit the Google form.
So can I ask you one more thing?
Yeah, sure.
In the lectures of topology in our NPTEL course, why have to study about non-linear space, metric space to uh, to know about topology? Why I'm not having any introduction videos in the beginning, but I'm having the definitions of metric spaces, non-linear space, so much of things. Why I have to start the course like that, sir?
So your concern is that there is a introductory videos, but you are the videos which still getting like starting from definitions, abstract definitions only. Am I right?
Yes, sir. Yes.
So by introductory videos, what do you mean actually?
I think the definitions of topology and the need for studying topologies and so much of definitions and the examples based on this. But when I'm seeing videos on those like a non-linear space, metric space, I can't compare with topology. Can you understand what I'm saying, sir?
Yes. I mean, you are unable to connect with metrics with normal with the topology. Am I right?
Yes, sir. It is totally different from our online classes, and the lecture is totally different. I can't connect with the both. I'm more comfortable with this online class than with the lectures. I don't know why this.
So can you tell me one thing? So I mean, do you understand this? Do you understand the fact that metric space? I mean, do you understand the fact that suppose we have a metric space, then that from that metric space we can give a topology on the space.
Yes, sir.
The point is that directly metric space and nonlinear space directly you cannot connect with topology via this abstract theorem. The only interesting fact is that from norm linear space implies metric space and metric space represents topological space. Okay, so that is the one-way connection. Now what I understood your problem is that you want more examples for understanding definitions. Am I right? Because the video lectures possibly lacks examples, isn't it?
Yes, sir. But for the beginners, I think maybe starting with the definition of topology and giving so much of examples, or maybe starting with the definitions or introductory videos on sets, functions, maybe more beneficial than these metric spaces, non-linear space.
Okay, so see, that function, the set theory which you are telling, those are the parts of algebra. The beginning of algebra is starting from the set theory, isn't it? I mean, so what is the exact problem? Just tell me, because this is not the. I mean, what is the exact problem? Tell me.
Starting with these non-linear spaces videos, I'm searching for the when will I'm going to study about topology. There are so much of lectures before the topology, the main topology lecture.
Correct only. Correct only.
That's the main problem for me. I don't know about others, but it's a main problem for me.
So the point is that I admit the problem and I understand that the lectures that has been created, it was quite confusing also because in topology lecture suddenly normally space comes, then that will create a serious level of confusion. I understand that, but lectures were created by faculty, so I have nothing. So I mean, I directly cannot do it with that. But what I can uh, tell you is that I mean the point is that whatever I mean initially in those lectures of nonlinear space, whatever is there, those are particular from nonlinear space. Those has nothing to do with the topology. Okay, so possibly also nonlinear space has some kind of inverse function theorem, closed graph theorem, and all, but those are nothing. Those have nothing to do with topology. Those are specifically to nonlinear space. Okay, So there is no need to connect, to be honest. Okay. And secondly is that if you are saying that initial things are like quite abstract, much of definition, so for that you need to practice some problems from any textbook, otherwise it will be difficult actually. And you were saying like some problem set theory. For set theory problem you can what is the problem in the set with respect to set theory, that I don't understand.
For a beginner, starting with the set theory and function is more beneficial. We can compare with the topology, right, sir? In the James Munkris textbook, also, he has started with the definitions of set theory, functions, and so much of things. Then only he has started with the definition of topology and the history of topology, so much of things. So I can compare with that. But in our lecture, I can't go with that. It's like mixing of
So tell me
in
one thing.
between
I
real
understand the problem. So tell me one thing that so so this course you are taking and the marks which you will get. So will this be counted in your college or university semester, or is this for your own interest only?
yeah, it's my own interest only, sir.
Okay, so that means the whatever the marks you will get in exam, that has nothing to do with the rest of your career. Am I right? Then only I will suggest one thing.
Yes, sir. You're right.
Okay. So, see, the point is that I know the problem you are facing. I also face the same problem. Many other students also face the same problem. Okay. And you told it with honesty. Thanks for that. The problem is that um, this lecture has been written down 4 5 years ago. Okay. I mean, those videos have been created 4 5 years ago. Okay. So, and then it has not been updated since then. Okay. So the point is that in the case when you feeling that these things are going to some another direction, you can stop there immediately. You can start from Munkres itself. Whatever the theorems he has discussed, most of the theorems is in Munkres. Okay. Yes, most of the things Munkres, apart from 2 3 theorems, mostly it is in Munkres. You can start read the book Munkres. It has done things very easily and smoothly, and it is Munkres is very beginner friendly. Okay. So if you are unable to follow something in lecture, you can forget that lecture. You can check the topic from the Munkres and start from Munkres itself. So that will help actually. Okay. And for what is that? Nominal space. There is a book called BV Limai or BV Limai. There is a book with function analysis. You can download the book over internet, and whatever the
Can you
topic.
text the book
Yes,
name,
yes.
sir?
1 minute. Let me write it down. Where is that? Oh God, where is that? Okay. BV. So the book is BV Limai by Functional Analysis. Sorry, Functional Analysis by BV Limai. So this book covers the. This book starts from beginning of function analysis. Okay. So if you cite and also for metric space. So I hope there is a book called Kumaration which you know. Am I right?
Yes, sir.
Yeah, so these are 3 books you can follow if you are unable to follow anything from lecture. You can follow these 3 books blindly. Okay, you may just the or else you can only get the topic from the lecture and go through those books. That will also fine. There is no problem. Okay, but if you think that if you will follow from the video, then it is extremely difficult, and that's a matter of time waste. I understand that, and also it is frustrating also. So you can better it's go you go through textbooks. It will help, I guess. I mean, it will be better, I guess. Not, I guess. I'm sure it will be better. These 3 books
Okay,
you can
sir.
follow blindly. Okay. And if you have any doubt or like if you are unable to find any topic from these two books, or there is some topic which you are unable to get from internet also, you can write an email to VTLTV. That email will come to me, so I will get back to you in that case.
Sure, sir.
Yeah.
And also, can you recommend any best book for studying partial differential equation?
The point
It's a
is,
cross question, I know.
no, no, the point is that I have not studied partial differential equation. Uh, I, I I have never studied partial differential equation apart from school. So I don't have any
Okay,
knowledge.
sir.
It's not that I don't know. Sorry. What I'm saying that the point is I don't know any reality. Also, it's not that you are asking from different subject. I don't know. I don't have any idea. I have not studied in graduation, post graduation.
Okay, sir. Thank you.
Yeah.
uh, for comparison, like I start reading, but it's like very extensive. Like, should I start with?
Yes, yes. The point. I mean, point is that Kumaresh book is a full metric space. So if you think like you will finish by 1 month, then it is difficult, right? The book has to be finished within a year, not a month, right? So
Yeah,
it looks small, but it has lots of material inside. So
there's so much problems.
there is so much problems in this book. Correct. So at least you can take like within 6 months you can finish half of the book. So the book, so up to compact connectedness, so compactness, connectedness, and first 4 or 5 chapter you can finish within 6 months. Then you can start the same thing in topology. Then I hope that will solve the most of the problem in topology.
Okay.
You can start, no problem. I mean, of course, this book contains lots of things really. Okay, okay. So let's get back to this problem. So this theorem tells that X is connected if and only if any continuous map from X to plus minus 1 is constant. So, so that's what the theorem is telling. So can you please try to prove?
Sir, in the forward proof, by considering X is connected,
Mhm.
whether I have to prove the function f is continuous or constant.
So forward direction means you assume f is continuous, and then from you to show that f is constant. So for the timing, assume f is continuous.
Okay, sir.
Okay, so let's stop for today. So this problem can be continued in the next session. Okay, or you can try it on home, and if you are unable to solve, then we will just, I mean, we will start from next session from this problem itself. Okay, so let's stop today here. Okay, because I have
Yeah.
to
Okay.
go to dinner. Okay, thanks, bye. I'm leaving the session.